So remember localization? So what we saw before is that because localization of one particle well, we know that the expectation of, take this kernel, right? This is going to be exponentially decaying in x minus y. Right, for some constant, I called it alpha, I think. Right, actually I can even sum, right, but I have something like this. And of course, I can try to do the same thing here. Right, imagine that I try to do the same thing here, right? So of course I get that this is upper bounded by e to the pi x2, y1, right? But now you hit onto something, is that you see it's the same randomness in these two operators, and it's the expectation of the product. So you cannot separate the expectation of this product because they are depending on the same randomness, right? But what you can do is, in the discrete case it's simpler, but you know that this is less than 1 because this is a projector. And that's the projector applied to a vector of norm 1. Right? So this is less than 1. So what you can immediately guess from that is that this is less than e to the minus c max of x1 minus y1 x2 minus y2. Right? Plus e to the minus c max of x1 minus y2, x2 minus y1. Right? Which you could also write, you can give this following simple bound, e to the minus c over 2, x1 minus y1 plus x2 minus y2 plus e of minus c over 2, x1 minus y2 plus x2 minus y1. Why did I write it in this way? It's because this is a function which is symmetric in x1, x2, and in y1, y2. Right? Okay, because when you invert this one, you get this one, right? This is also symmetric, right? This is symmetric too. And which is natural for the expectation of something. This one is symmetric because I take the modulus, right? So I don't get any change. Okay, when I do the inversion because of this modulus. And so you see that for the free case, so this gives you an exponential decay. Right? So what is x1, x2? These are the two particles, right? And these are two other particles. And what you see is that when you take this group of particle away from that group of particle, the thing decays exponentially, right? And this is why you can say that this would be a nice definition for localization in the many particle setting. You take two groups of particles, take them apart from one another, and you should see exponential decay, right, in the distance between these two groups. But of course, you have to respect the symmetry, because exchanging these two particles doesn't change the state, because you're dealing with anti-symmetric functions, right? So it's not the distance, it's not just this distance or that distance, it's really the sum of the two. You need both of them, right? To take into account the fact that you are interchangeable particles. These two particles are interchangeable, and these two as well. Okay?
Distance between clusters.
Exactly, it's distance between clusters, right? But in the cluster, the two particles can be interchanged. Right? So this, you could say, for example, that the state is localized, right? An n-body state is localized if it satisfies something like this. And so the whole question is now, imagine that I take the ground state of my operator with interaction. Is it localized or not? Right? It is in the free case, as one expects, but is it still in the interacting case? Okay, let's come to that question. And to actually give an answer to that, well, I need a more specific model. So I'm going to use a 1D toy model. Which actually was studied by physicists in the one particle case. And it's the following. On R, you consider a Poisson process of intensity 1. What does it mean? It means that you throw randomly, independently from one another, points on the line so xj of omega. There are infinitely many points on the line, thrown in such a way that they are independent from one another, right? And such that the average number of points in an interval of unit length is equal to 1. Okay? So one way to do that is, for example, take the interval minus n, n. You throw 2n points uniformly distributed on minus n, n, right? And you let n go to infinity. And the picture that you get is exactly this Poisson process. So take such a Poisson process. And now fix minus L, L, right? And this is lambda. This is lambda. Okay? And at each of these points, at the end points, but also at each of these Poisson points, right? You take a Dirichlet boundary condition. So you take xj of omega, that is between minus L and L. You can actually imagine that this is strict, right? You take all the j's, such that, so the number of these j's and what they are will depend on omega. This is a random thing. Okay, take all these j's. And you look at set, so let this be j minus j plus, right? You take this to be the integer interval j minus j plus, right? J plus minus j minus is equal, plus 1 is equal to what I call m omega, so it's the number of points in there, right? That's the number of points in there. Okay? And what you do is you consider the operator h omega lambda to be the direct sum. So set x, set j minus 1, sorry, x of j minus 1 to be minus L, and xj plus 1 to be L, and consider the number, so consider the following thing. Take from j going from j minus 1 to j plus of just the Dirichlet Laplacian on the interval xj omega to xj plus 1 of omega. Just take the Dirichlet Laplacian on this. So what it means that I put Dirichlet boundary conditions right on each of these points. Okay, so this is not a Schrödinger operator, it's something more complicated. Or more simple, actually. It's not more complicated, it's more simple than a real Schrödinger operator. Right? It's a random operator. But the nice thing is that the spectral theory
J plus 1, right?
sorry? No, you have to J plus, and this is here you get, yeah, this is 1 plus 1, yeah, exactly. This is plus 1. The spectral theory is completely known, right? Because you know this is a direct sum, right? And so this is on L2 of lambda, right? You just write L2 of lambda as being the direct sums of the L2 on these spaces, right? And each of these spaces, of course, you know what the eigenvalues and eigenvectors of the Dirichlet Laplacian on the interval is, right? This is well known, easy to compute. And now, from this, you do the following thing. So this is a very localized operator, right? This is very localized. Why? Because the eigenfunctions of these operators are exactly functions living on one single interval. They do not only decay exponentially at infinity, they are just compactly supported, right? So it's very localized in a very strong way.
In a sense, it's just an artificial problem. Yeah?
It's a toy model. It's a toy model, right?
No physics which...
No, there is no real physics, right? Because each of these particles is inside its box. But once you add, so you now look at h omega 0, right? N lambda in the same way. You take n particles, right? In the same way. And you pick u going from R to R plus, right? Assume bounded and compactly supported. And in the way we did before, you define H, U. So this is as before, right? It's just my H omega, not restricted to lambda, it's comma lambda, tensor 1, tensor lambda, right? This is H0 without interactions. And then you take HU n omega lambda to be H0 n omega lambda plus the sum of u of xj minus xj, I less than j, from 1 to n. Okay, and let psi of u n omega lambda be a ground state, because I'm not sure that the ground states are unique, right? Be a ground state of hu n omega lambda. And the theorem is the following. There exists theorem, there exists rho 0 positive, such that there exists some L 0, such that for L larger for L larger than L0 and N over L less than rho 0, right? If I look at the expectation of the gamma 2 of psi u n omega lambda, right? I look at this, then this satisfies that it is less than, so there exists some constant C0 positive, right? Actually, it satisfies. So I look at this. This is again a kernel, right? x1 minus y1 plus x2 minus y2 plus e to the minus c0 x1 minus y2 plus y1 x2 minus y1. So with the interaction, you have the exponential decay, right, for the gamma 2 of the ground state, as you had it for the free ground state. So you can say something about the rate C0, right? I don't want to go into this. It's not the main thing, right? The thing is really that the ground state is exponentially decaying, so it's localized according to our definition. Okay? Which is one of the definitions that the physicists found. Okay?
Can you see some effect of randomness in this toy model?
Well, the toy model is random. No, but this is an effect. The fact that this be true is an effect of the randomness. You wouldn't have the same thing if you didn't take random intervals.
Yes.
Okay, this would not be true.
Okay.
The expectation that this satisfies this comes from randomness.
Okay.
Right? So imagine that I cut things, all the intervals are the same of like length 1.
Okay.
I don't get this result. This would be false.
Okay.
The fact that this is true really comes from the fact that here you have a random process. Right? This is an effect of randomness. I agree with you that localization here is not an effect of randomness. Right? It just comes from the fact that I have cut off. But that it will be localized in this sense here with the interaction comes from the randomness. It would not be true if I take intervals that are not randomly distributed. Right? Okay. So.
One cluster far from another.
Sorry?
One cluster is far from another.
Yeah, exactly. The ground state, in the ground state, indeed, where are the n lowest eigenvalues for this one? They are in the n largest pieces, right? There are ground states of the n largest pieces that you find here. And because the thing is random, these pieces are not close together. They are pretty far away from one another, right? And this is really this randomness. So if you take all the pieces to be of length 1, there is huge multiplicity in the ground state, but even if they are of lengths close to one another, then you change the n, but they could be close together, right? And it would change the shape of the ground state completely. And the ground state in the 1D case, right, if you take a one particle model, this is actually very close to a 1D operator. Imagine that I take a 1D operator, right? Instead of taking hard walls here, I take just a bump of potential at these Poisson points, right? When I look at low-lying eigenvalues here, these walls look very much like those. Not exactly the same, right? Because there is some tunneling through this. but there's very small tunneling. Right? So this is actually, in a way, quite close to the true random model. It's not the same. Of course, technically, it's much easier to deal with.
Okay.
Okay? But it bears the same characteristics as the true localization. Okay? But indeed, the fact that this decays exponentially does not come from the fact only that the spectrum is localized here. It comes from the distribution of these points. Right? And without this, it wouldn't decay exponentially. If you distribute them with only intervals that are close to one another, you'd get a huge states which would be more or less extended. But this does not happen because of the randomness. Right? Or it happens with only very small probability. Of course, it's not excluded, right? But it's very highly unlikely. Okay. Now, so this is for the theory at what is called zero temperature, right? So you look at the ground state. But you can do, which is something that physicists use readily, right, is look at what's happening at positive temperature. Okay, you want to understand what is happening because you're doing quantum statistical mechanics and you want to understand what's happening at positive temperature. What does it mean mathematically? Mathematically, it means that you do the following. Instead of looking at the exterior symmetric product of L2 lambda, right, that are called Hn, you are going to look at the following thing. You are going to look at the direct sum of Hn when n goes from 0 to infinity. Call this H. Right? So this is a huge Hilbert space. You can have there as many particles as you like. Okay? And on this, you look at the operator, which is just going to be the direct sum. So the operator H omega, sorry, I had the U. There is no L and there is omega lambda. There is no N. It's just going to be the direct sum for all n positive. Okay? Of course, for n equals 0 here, this space is just the complex numbers. And this is just the identity operator, right, for n equals 0. So it is HUN omega lambda. Take a look at this. Okay, so this is a huge operator. In each of these sectors, you have this operator acting. Okay? And then you look at the operator e to the minus beta, and you take H omega lambda u minus n. It's actually this, well, I'm going to change this. I'm going to take this one n, this one little n. I keep the large N for something else. Capital N I keep for the operator, the number operator. This is an operator that goes from H equals to sum. Right? It goes to itself, okay, to H, and to phi, sorry, n larger than 0, to phi, which is phi n larger than 0, it associates n phi n. It is just a number operator. Right? You multiply by the number of particles. So if there are 0, it's 0, 1, 1, and so on. Okay, and take this. And here, sorry, I forgot something. I forgot mu for mu positive. Define this, right? And what you look at, so this is the Gibbs state. G, it depends on omega, lambda, u, and mu. This is what is called the Gibbs state in the grand canonical ensemble, right? For this system of particles. So you don't restrict the number of particles. It can be any number of particles, but you actually control it using what is called mu is called the chemical potential. You control it using the chemical potential, right?
Constant, right?
Sorry? Mu is a constant, exactly. And the Gibbs state should be normalized. Actually, I forgot to normalize. You can show that this is a trace class operator, and you normalize by exactly the trace of this operator. Right? You normalize by this huge trace. Okay. And then, for this state, right, you can again.
What is the physical meaning of this Gibbs state?
Well, this Gibbs state is, the physical meaning is the following. It gives you the distribution. Once you fix the temperature, right, it gives you the distribution of the number of particles at chemical potential mu. Right? So beta is 1 over temperature. Right? At a temperature T, it says that things are exponentially, the probability, right, that you have low temperature is exponentially small. So in particular, if you let T go to 0, right, and you look at this, you see that, well, this is a computation to be done. It's not completely obvious, right, when you see this. You see that when you let T go to 0, you have a convergence towards this operator at a certain density of particles that depends on mu. Okay? Because roughly this function here, because of this division, is going to look more and more, this exponential is going to be sharply peaked at some value, right, that depends on mu. You have a rho mu. So n, when it's above rho mu, this is going to be very small. And when it's below rho mu, it's going to be very small. So you're going to get something very peaked, and it converges to such an operator at a density rho that depends on mu. Okay? And when T goes to 0, beta goes to infinity. Sorry, beta goes to infinity, right? Beta gets large. And the theorem is the following. So you can do the gamma 2 in the same way as before. You just do the gamma 2 for all n larger than 2. Take all n's larger than 2, and you take the gamma 2, and here you get the direct sum of the gamma 2's that you get. Right? The two-particle operator, two-particle density matrix. You can do sector by sector, right? Meaning for each n. Of course, for n equals 1 and n equals 0, there are no two particles because there's a single or no particle in the system. But starting from n equal 2, you have two particles at least in the system, and you can compute the gamma 2. Right? So this way, you can define the gamma 2 of your Gibbs state of G. So let me put it here. Of G omega n u n, right? Again, it's an operator. Right, so it has a kernel. Okay, now it's because you've restricted to two states, you sum these kernels, right? They're always operators acting on the tensor product L lambda tensor L lambda, exterior tensor product. So the theorem is the following. There exists some mu0 positive and some constant such that for mu less than mu0, right? I need to check something here. Because there is a dependence in the temperature. Exactly. So that there exists some function C beta that sends beta positive, right, from to the which is an increasing function on the beta positive to R plus, right? C beta is increasing with temperature, such that this is less than C beta e to the minus C beta let me think, yeah. x1 minus y1 plus x2 minus y2. And same thing, plus e to the minus c beta x2 or x1 minus y2 plus x2 minus y1. Okay? So you have the same kind of exponential decay at positive temperature for the grand canonical ensemble, right? So the C beta doesn't go to infinity, right? It's just there is some limiting value when beta goes to infinity.
It goes to infinity.
No, it doesn't go. It goes. It's increasing and goes to R plus. So if you want, the idea is that the C beta gets worse and worse as temperature gets larger.
Okay.
Right? When temperature gets larger, T large, beta tends to 0, right? And the C beta is getting smaller and smaller, right? But the natural thing is that C beta tends to the value that you have here. That you had here before on the previous slide. This I don't know actually. The only thing I know is that it's an increasing function of beta.
So if the temperature goes to infinity, the things become more and more delocalized.
Exactly. As temperature goes to infinity, things become more and more delocalized. Exactly. That's exactly the point.